Okay, so we are on to the last topic of lecture 9, real gases. Okay, so I mentioned to you earlier on a different video that the molar volume of a gas is basically given here on the periodic table, right, for the gaseous elements. And we see that the values are kind of close to each other in the vicinity of, 15 and 20, roughly speaking. They're kind of close to each other, but the key idea is that they are not the same. And I show you that for an ideal gas, the molar volume, as well as the concentration of the gas, as long as you keep the temperature and pressure the same, the molar volume of a gas, irrespective of what the gas is, will remain constant. That's what the ideal gas law tells us. And yet, looking back at the periodic table, we see that that's not the case at all, right? Like, look at the worst case here, 50.5 cubic centimeters per mole versus 11.42 cubic centimeters per mole. That cannot be confused as saying that, yeah, they're roughly the same. That's not roughly the same. That's pretty off. The percent error right there is huge. And this is nothing more than saying that the ideal gas law is based on two premises. The premise is that the gases themselves don't have any volume of their own, and the premise that there is no interactions between gases. Those two ideas that surround the ideal gas law are indeed wrong. And this is the reason why the molar volume is not constant when you actually look at experimental data for the gaseous elements. So we're going to have to redefine the ideal gas law somewhat to account for the fact that gases are not point particles. They actually do have a volume of their own. And when you increase the pressure, if you increase the pressure just high enough, at one point, the gases are so close together that their own individual molecular or atomic volumes get in the way. And you can have two atoms on the same actual space. And we're talking now the atomic space itself. So we're going to have to account for that. And as it turns out to be the case, you may recall from your discussion of intermolecular forces from previous chemistry courses that molecules can actually interact with one another. And that's kind of what keeps them together in a bulk sample. So these interactions will prevent, in some instances, if they are attractive enough, as intermolecular forces tend to be, this will keep the molecules from expanding as far away from each other as they can possibly do so. And the actual volumes will be a little bit less than what you would expect ideally. So we're going to use the van der Waals equation of state of real gases to depict this, this problem. The idea that gases are not point particles, and the idea that there can be actual attractions between gases within a sample. And the reason we tend to stick with the van der Waals equation, at least at this level in chemistry, is because it follows a format that is very similar to the ideal gas law. If you look carefully, here we have pressure plus some term times volume times some term equaling RT. Now, specifically, this is not regular volume, but this is rather the molar volume. And what I was telling you in an earlier lecture video is that the volume needs to be now determined, the molar volume, excuse me, needs to be determined specifically by dividing volume with the number of moles of gas. Okay, that's going to be the key. You first need to find out what the molar volume is simply by dividing volume with moles, and then you input it into this equation. But in essence, this is the same thing as the ideal gas law, except that we have some correction factors. Specifically, A divided by the molar volume square is the correction factor for the intermolecular forces, because the idea right here is that we're adding an extra temp to the pressure. We're going to have a slightly higher pressure. We're going to have a specific higher term for the pressure because of this intermolecular force of attraction. Okay, so we're kind of accounting for that there. And over here, subtracting the amount from the volume tells us a little bit about the fact that the gases do occupy a volume of their own. So you actually have less volume available in your receptacle than you think. And intermolecular forces, attracting gases together, means that your pressure is not exactly what you think it is ideally, right? So with these two correction factors, we are going to account for the fact that internal forces are present and the fact that the gases do occupy some volume of their own. All right, now the thing is this: A and B are constants, and these constants depend on the identity of the gas. They actually do differ from gas to gas, and as such, they need to be given to you in a problem involving real gases. Okay, so for instance, if you're dealing with 1 mole of CO2 gas, which happens to occupy 536 mLs worth of volume and 373 Kelvin temperature as far as the setup, we want to calculate the ideal and real pressures. And for the real pressure, we have to be given the value of A as a constant and the value of B as a constant. This is directly related to the identity of the gas itself. And this is a value that I'm going to have to give you. I could potentially have you calculate it, but I will have to give you everything else present in the van der Waals equation for you to get the values of B or A. But right here, we're trying to find out the pressures, the ideal and the real pressure. We're going to compare them to each other to see what the deal is. All right, now we know that ideally PV equals nRT. If you divide both sides by moles, you find out that P times the molar volume equals RT. That's still the ideal gas law. And here on the right side, we have the van der Waals equation for real gases. P plus A over molar volume squared times molar volume minus B equals RT. All right, so first thing that we need to do is determine the molar volume, right? Oh, and by the way, since we're looking for pressure, we need to solve for pressure. For the ideal gas law, that's relatively trivial. Divide both sides by the molar volume and you get the ideal pressure. For the van der Waals equation, what you first need to do is divide both sides by molar volume minus B. All right, so that's what's happening right here. And then subtract A minus the molar volume squared, which is what we have right here as a term. If you were to subtract first and then divide, this will be all messed up. The division needs to happen first because that's on the outermost portion of this equation. The subtraction happens last because it's inside the parentheses. Okay? All right, but the molar volume needs to be found. And in this problem, you have 1 mole specifically. So the volume of the gas divided by the moles is going to equal exactly this value. But in other problems, I might tell you that you have 0.75 moles, or you have 0.25 moles, or you have 0.33 moles. As long as the moles are not equal to 1, the volume divided by moles will not equal 533. So, case in point, here I've gone ahead and determined the molar volume by dividing the volume in liters. So I change the mLs to liters, divide this by 1,000 to get 0.536 liters, and then I divide the 0.536 liters by the number of moles. In this example, I only have 1 mole. In future examples, you will have numbers different from 1 mole, so you actually gotta do the division. 0.536 liters will have to be divided by whatever the number of moles is. That number will be what you enter as the molar volume. Okay, but here what you can see is that we have the gas constant, the regular gas constant, 0.08206 atmosphere liter per mole Kelvin, times the temperature, which is 373 Kelvin, divided by the molar volume, 0.536 liters, right? And that equals the ideal pressure. Over here, we have to input the gas constant, 0.08206, atmosphere liter mole Kelvin, or in other words, atmosphere divided by molarity Kelvin, multiplied by the temperature in Kelvin, divided by the molar volume, which is liter per mole or inverse molarity, minus the value of the B constant. All of that gets subtracted by 3.61 atmosphere per molar square, which is the value of A, and that gets divided by the molar volume square. And so what you have to do here is take the molar volume and square it. That will also square the unit of molar volume, which is per molar. Alright, so the kelvins cancel out in both equations, and in the ideal gas law, the moles cancel out, the liters cancel out, and you end up with just atmospheres. Over here, you're going to have to do a little bit more calculation to find out what cancels out, but ultimately, the 1 over mole or per mole cancels out in all of this stuff, right? And the per mole square will cancel out on the second fraction, and you'll have atmospheres and atmospheres on both sides of the equation. Carrying over the calculation for the ideal gas law, we find out that the ideal pressure is 57.1 atmospheres. Over here, taking care of the first fraction for the real gas law gives us a value of 62.1 atmospheres. And the second fraction, once you square the 0.536 and divide it from the value of A, which is 3.61, we get 12.6 atmospheres. Finally, taking care of that subtraction gives us the real pressure of the gas, 49.5 atmospheres. And notice that the real pressure is lower than the ideal pressure because the gases are attracting each other, keeping themselves from expanding all the way outwardly to give you excess pressure. So the real pressure is actually a little bit lower than what you would expect it to be. All right, and this is roughly how the problems are going to turn out, but I really can't overemphasize the idea that the molar, the molar volume needs to be calculated first before you attempt to start solving the van der Waals equation. Divide volume by the number of moles to get the molar volume, and they input that into the equation. And don't forget to square the value of the molar volume for the second fraction of the van der Waals equation. Lastly, the value of R is 0.08206 because we're dealing with pressure. And anytime you deal with pressure, this will be the value of the gas constant. The value of the gas constant being 8.3145 will only apply when we deal with kilograms or when we deal with values of energy, joules. I'll talk about that in more detail on a later lecture. For now, this is the end of the video.